Alright, silly people, here's the situation. We have a resonant cavity that is a cylinder with radius r and length L that we're going to be propagating waves through and figuring out what the resonant frequencies are um, for this guy. So, without getting too into the weeds, I will just write out what the general wave function for resonant cavities and cylindrical coordinates are. Um, and I'm going to be doing Tm and Te at once. So for Tm, it's cosine kz, and for Te, it's sine kz. Uh, and this is going to be sum over L and M to infinity. You're going to have your Bessel functions, which are functions of gamma and rho. I should move that bracket. And then with your angular dependences, ALM e to the im phi plus BLM e to the minus im phi. And that those are for TM, TE modes, where gamma LM means different things depending on which mode you're looking at. If it's TM, then it's XML over R, and this is going to be X prime ML over R for TM and TE modes. And then what are X, ML, and X prime and L? Well, those are the Lth roots of the Bessel functions and also the Lth roots of the primed Bessel functions, the derivatives of those. And gamma also has this relationship with resonant frequencies as being the square root of mu epsilon omega squared minus k squared, where because we have these boundary conditions where the waves and the electric field, the longitudinal component has to be 0 at the caps, and so the derivative of the magnetic fields have to be 0 at the caps as well. So that kind of places a value on the wave number to be pi over L, where p pi over L, where p is either a natural number or 0. Okay. And so solving this equation for the frequency, you can express the frequency indexed LMP, because now we have another integer to look at. It's going to be 1 over root mu epsilon. You'll have the square root of 1 over r squared. And then depending on TM or TE modes, you're going to have a XML squared here, or an X prime ML squared, plus your wave number squared, and that is for TM and TE modes, where P is either a natural number or 0. Okay. So the problem does ask us to plot the 4 different minimum frequencies, and I'm going to avoid degeneracy here because obviously, like TM and TE modes, some of them will actually share frequencies. And I'm just going to look at the 4 lowest ones then that aren't degenerate. So those are going to be for TM. I'm just going to pick the lowest 2 of these. It's going to be omega 111 and omega 121. And for TE, it's going to be omega 111 and omega 211. And I'm going to write up on the screen how to calculate both of those, or all four of those, um, as functions of the roots of the Bessel functions. So for Tm, that's going to look like omega 111 will be 1 over root mu epsilon. You'll have the square root of x11 squared over r squared plus pi squared over L squared. Yeah, I picked P is equal to 1 for all of these because the problem does want it in units of R over L, and L just doesn't show up if you choose P is equal to 0. So non-trivial P, I guess. You can factor out a 1 over R from this radical. So you can say this is the square root mu epsilon, and then it's just going to be x11 squared plus pi squared r squared over L squared under a square root. And then so using that equation, you can plot omega 111 as a function of r over L in the units of 1 over r root mu epsilon. And then you can, I'm going to be doing that later, and also I'll just write out the rest of these equations for the frequencies. Omega 121 then will be 1 over root mu epsilon. You have the square root of, this is going to be x12 squared. You're going to have pi squared r squared over L squared. Then for TE, omega 111 will be 1 over r root mu epsilon, and then square root of x prime 11 squared plus r squared pi squared over L squared, and then omega 211 will be 1 over r root mu epsilon, square root x12 prime squared plus r squared pi squared over L squared. Right, those are your frequency equations. Before we move on to plotting, I'll note that the next part of the problem asks you to compute a factor of Q for the resonance cavity, which is supposed to model the power loss. And for our cylinder, that's going to be given by mu sigma omega over 2. That is the formula for 1 over the skin depth. You have L up top, and then in the denominator you have 2, 1 plus some number C, which is on the order of 1, which I'm just going to approximate to 1 because I don't actually know what Jackson is talking about. And then it's going to be the circumference of your waveguide, which is 2 pi r times the length, and then you have a 2 down here, as well as, actually no, it's a 4 down here, as well as the area of your cross-section of your resonant cavity, which is pi r squared. All right. So, I mean, we can simplify that as well. And that's going to be mu over mu c root mu sigma omega over 2 L over 2 times 1 plus just L over 2R. Okay. I'm also going to make the approximation that the permittivity of copper is really, really close to the permittivity of free space. It's a pretty darn good conductor. And so that will just pretty much just get rid of the mu factor out front. And then you'll have this stuff. Just 2 plus L over R. That's going to be your Q factor. Now I'm going to seamlessly transition into the graphing part of this and make sure that it doesn't look awful. It looks awful. It's probably as good as it's going to get. So I'm going to use Python to get a graph of this stuff. Let's import the relevant packages. So let's do NumPy. Let's do matplotlib. It says to plot it from the range R over L 0 to 2. So let's create a domain for ourselves, which will run from really small, so 0.01 to 2 with 100 samples, because why not? I found online that the roots of the Bessel functions that we want are going to be 3.8317, x12 will be 7.0156. Those are the roots, the first and second roots of the first Bessel function. My cat's being noisy. And then the first root of the derivative of the first Bessel function will be 1.8412, and the first root of the derivative, or the second root of the first derivative of the first Bessel function will be 5.3314. We'll define a general equation which will calculate the frequency as a function of the root and also the ratio from R to L as being the square root, so NP square root, and then this was we had x squared plus just the R squared, and then it was multiplied by pi squared, so star np dot pi squared. Alright, that should work. Then we'll just plot a bunch of lines, R sub L, and then we'll do our function, which is going to run for the first Bessel function thing, and then R sub L will be its R value. We'll set the color to red, and we'll label it TM11. And then we're going to do this a number of times. So just say bam, bam, bam. Except this will be 1, 2. This will be dx11. This will be dx12. Let's make this one black, this one green, and this one blue. And this is the TM12 mode, this is the TE11 mode, this is the TE12 mode. Right? We'll set up a legend, or we'll set up a, oh my goodness me, I'm terrible at writing code. We'll set up a legend to show up on the graph, the plot. We'll set up a X label. It's the X values have just been representing the ratio of R to L. So R to L, and then the Y value will be omega times R over C. Those are the units of omega that we're working with. Okay, so it should plot now. Let's run it in the plot window. Okay, so it looks like these are our frequencies plotted against R over L. So it looks like TE11 seems to have the lowest frequency across the whole range of R over L, which means in the next part where we calculate the Q value, let's use omega 11 in that equation. So we'll have our Q was equal to NP dot square root. The permittivity of free space is 4 times pi times 10 to the minus 7. The conductivity of copper was just 5.8 times 10 to the 7. That's in units of sieverts per meter. We need to actually set up what the values of R and L are. In the book, Jackson wants us to do R set to 2 centimeters, L equals to 3 centimeters. And we want the frequency of the lowest TE mode, which was DX 11, and then R over L here, getting it through our function. And so you want to multiply the stuff in the square root by your omega value and then divide it by 2. And then this fraction is just L over 2 plus L over R, or L over R. Match the cases. And I think that should be good. Let's give it a run. Oh, let's actually make it print out the value of Q. And then now let's give it a run. Okay, so yeah, I think this is fine then. So this is your value of Q for this resonant cavity. It's 0.0864. That is for the TE11 mode. All right.